All right, welcome everybody. In this video, I want to introduce you to a very useful graph that is called a slope field, also called a direction field, that we can use to approximate solutions to differential equations, even if we don't have a formula for the solution. So what you are looking at right now are examples of slope fields. You got three different slope fields. So in this video, I want to discuss how we can create and read these slope fields using Python. And so to begin with, I want to just direct you to where you can find the materials that we'll be working with in this video, which is a Jupyter notebook that is called 0 to slope fields that we're working with in Google Colaboratory. So to begin, here's where you would go, would be to the Colaboratory main website, and I will box that in up here. So the address is colab.research.google.com, and that's going to take you to a launching window that looks something like this. The default is you're probably opened up on the recent tab and looking at some files that you might have recently been working with. Where I want to go is to this tab over here, which is GitHub. So these files are stored in a shared file repository on GitHub. And so the GitHub URL, where to find these materials, you would enter just as you see it on the screen, and that is CU-Denver-MathStats-OER. And you just want to pay attention to the capitalizing and placement of the hyphens in that URL. And that's going to bring up a drop-down menu below where you can choose from different courses that we have in our GitHub repository at University of Colorado, Denver. And the repository for this course is right here, ODEs for ordinary differential equations. And so when you click on that repository, you'll see all of the worksheets we'll be working with this semester. And the worksheet for this video is slope fields. But rather than click on the name, I'm going to click on this little icon over here, which is going to open it in a new tab in my current web browser. Okay, so after I click on the option to open in a new tab, I would get taken to a window like this, where we're now looking at the Jupyter notebook in Google Colaboratory. And you can see circled in blue on top the title, the slope field, and you can also see that little black icon is indicating that this is actually not your own version of this document, but the shared version in GitHub. And so you're going to want to edit this file and save your own personal copy into your drive. So there's a button just below that's called, that you can see says copy to drive that I've circled in red. And so what you would want to do is click on that button to create a fresh copy that you can then have permission to edit. Okay, and so now you can see on top that I've got a fresh copy of the slope field that you can rename and move around to store anywhere in your Google Drive. And so here's the worksheet that we're going to work with. And I am going to skip running these first two code cells. What you would use these two code cells for, this first code cell is going to see whether you're running Colab or you're running this on another application such as Anaconda, and then depending on what application you're working with this worksheet in, you could run this cell to create interactive plots. I'm not going to need to use interactive plots in this video, so I am not going to run those two lines of code. So here we are. First, let's define what a slope field is. So a slope field is a graphical representation of a rate of change, a differential equation. So for example, let's take a look at the differential equation below. dy dt is equal to y plus 2t. And so if I am creating this graph, and let's say I want to know what am I going to plot at the 0.13. So I'm just approximating the 0.13 over here. Well, at the 0.13, I'm going to plug in t equals 1, and I'm going to plug in 3 for y, and evaluating that equation gives me a slope dy dt of 5. So at the 0.13 in the slope field, we would plot a vector whose slope is approximately 5. In this case, I've drawn an upward sloping vector because at least I know this is a positive value. So let's take a look at this first example, question 1 below. And so here we're going to be working with the differential equation dp dt is equal to 0.8p. So I'm going to set up a little table down below, and then I'll show how we could enter this into Python to get a graph of the slope field. So at each point, we have coordinates t, p. And what I'd like to do is calculate the slope dp dt, which is equal to 0.8p. So for example, we can pick a point. Let's pick the point at the origin, 0, 0, and then to figure out what we're going to get for the graph, and I'll draw this graph, or at least a rough approximation for this graph over here. So I'm at the origin. Then what we're going to plot is a vector whose slope I would get by plugging in t equals 0, p equals 0 into the differential equation, which would give me 0 in this case, because 0.8 times 0 times p equals 0 would give me 0. So in the slope field, I just draw a vector at the origin whose slope is 0. So in this case, that would be a horizontal vector. And we could continue on to other points. So for example, at t equals 0, p is equal to 2. I'm going to plug this point into the differential equation. And notice the value of t does not make a difference. And since the value of t is not in the equation for the differential equation, we call this differential equation autonomous. And again, autonomous means it does not depend on the independent variable t. It only depends on the dependent variable p. So I plug p equals 2 into the differential equation, and I get 2 times 0.8, which gives me a slope of 1.6. So at the point 0, 2, I would draw a vector whose approximate slope is 1.6. And let's pick one more point to illustrate this. If I were to evaluate the slope field at the point -1, -1, t equals -1 doesn't go into this autonomous differential equation, but p equals -1 would give me a slope of -1 times 0.8, or -0.8. So that point might look like a vector which has a small downward pointing slope in this case, because the slope is negative. Okay, so now we've shown how we can figure out the slopes of the vectors that we want to plot in the slope field. Now I want to illustrate how we could get a sketch of the slope field, at least a partial slope field in Python. And in class together, we'll talk about how we could generate a complete slope field without having to enter individual vectors. But for the purpose of understanding the concept of getting our foundation with slope fields, let's just first talk about how we can compute, plot slope fields in Python. So I'm going to run this code cell over here by clicking the play button, and that's going to run the code. And while that is running, let me just explain what this code is doing. The code finished. It didn't take very long to run. And that is each of these commands, plt.quiver, is going to plot a vector in a slope field. So I'm going to import the matplotlib plotting package, and inside plt.quiver go 4 values. So first goes the value of the independent variable t. Next goes the value for the corresponding dependent variable p. I leave the next entry, which is the change in the independent variable dt, to be 1, and therefore the slope that I'm going to add, I enter in as the 4th entry for dp. And so at 0, 0, we found the slope of 0, and so that's why I have a 0 over here. At the point 0, 2, we found that the slope was 1.6, so I enter 1.6 for the 4th value. At -1, -1, we found the slope of -0.8, and so that was going on here. And I don't need to edit anything else in this code. And down below, you can see we've got the slope field plotted that matches the rough sketch that we drew by hand pretty closely. We've got a vector that has slope 0 at the origin. we have a vector whose slope is 1.6 at the point 0.2, and we have a downward sloping vector with slope minus 0.8 at the point -1, -1. Okay, so now we've got an idea of how this process goes for creating slope fields. Let's fill in a few more vectors just to make sure we're comfortable with this. And I want to show you how we can also edit some of these markdown cells in this Jupyter notebook in Colaboratory. So we've identified a couple of vectors. Let me fill in a couple more. And so there's nothing special about the points I'm picking now, but let's say, for example, I pick next point at -1, 0. Recall the value of t doesn't make a difference here because this differential equation is autonomous, but the value p being 0 means our slope would be 0. If I were to lastly say what is the slope of the vector we're going to draw at the coordinates -2, -3, I plug -3 in for p, and that gives me a slope of -2.4. And so now this question 1a is asking me to enter some additional vectors into this table, which was created in this markdown cell. And so if I want to edit this cell, I just double click on it. And now it goes into edit mode, excuse me. And so now you can see that I see the kind of raw markdown and the rendered markdown on the right. I've got some writing over this stuff on the right for now, but I want to leave that table there. But if I want to enter the next value that we found on the slope field, which was at t equals -1 and p equals 0, I just type them in to the table, and that gave me a slope of 0. And the next vector that we entered was the vector at -2, -3, and that had a slope of -2.4. And if I want to see what this output looks like, or what this markdown looks like when it's rendered, when it's formatted, I just can hold the shift and the return key, and out comes the rendered markdown, and you can see the next 2 rows of the table were filled in. So I'm not going to fill these all in while I'm recording. So instead, I'm going to take us over to solutions that will then wrap up this video. Okay, so now for this solution, you can see I've plugged in a couple more vectors, and there's nothing special about these vectors that I've chosen. I filled them in on the table, and down below, we've got Python code that has them all, those additional, so the first 3 vectors are entered up here. I haven't changed that. I've entered in 5 additional vectors that I entered in the table above, and we can run this code and see the corresponding output down below. And as I mentioned earlier, in class, we'll use a really nice function, which is going to plot tons of vectors in our slope field all at once, so we won't have to do this one by one. But in the interest of getting some understanding of how to create and interpret these slope fields, I wanted to plot some individual vectors. But now let's make some observations about the larger picture. And recall that this differential equation was autonomous. It did not depend on time t. The differential equation was dp dt equals 0.8p. So that means given a fixed p-value such as p equals 2, if I move across this horizontal line through p equals 2, they all have the same value for p, although different values for t. But since the differential equation only takes p as an input, they're all going to have the same slope, in this case, a slope of 1.6. So I know that along this horizontal line, we're going to get a bunch of vectors that are approximately horizontal. The same goes if we were, say, fixed at a p-value of -1 down below. All of these vectors are going to have the same slope, -0.8. So I would get a bunch of parallel vectors along that line. And one other type of solution that we have in this differential equation is if we start with a p-value that is equal to 0, notice these slopes are all 0, so that means the value for p is never going to change, and that solution just looks like a horizontal line, p equals 0. And this property that we've been talking about the vectors being parallel along horizontal lines is not always a feature of slope fields, just in the cases when the slope field is autonomous, when it's independent of time. Okay, so lastly, question 1b below is asking us, now that we have a slope field, how could we use it to sketch approximate solutions to the differential equation? So I haven't found a formula for any of the solutions, but I've got this nice graphical representation. I have some observations about a solution that would start with a positive p-value, and that is that the slope dp dt is always going to be positive. And as p increases, the slope is going to get more and more positive, meaning it's going to get steeper and steeper and steeper. So if I were to start with a small population, a small value for p, this solution is going to go up because dp dt is positive. And as we move to the right, it's going to get steeper and steeper and steeper because dp dt should be getting bigger and bigger and bigger. So here I can draw an approximate solution that looks like this. And notice those vectors in blue are approximately tangent to the solution that I've drawn. If we were to start with a negative p-value, we could read this slope field in a similar way, but we get a solution that has different behavior. This one has dp dt being negative, so these solutions would decrease. And a third type of solution is the solution that we've already talked about, and that was the solution that if we start with p equals 0, the solution through any one of those points is going to be a horizontal line, meaning p is going to always stay as 0. So even without knowing formulas for the solutions, we're able to give a really nice description of all of the solution types, whether p starts with something being positive, p starts with being something negative, or p equals 0.